Hello everyone. This video is going to be a bit, it's not that complicated, so things are going to be quite simple today. We've talked about linear equations and some examples on how they were used in real life. In this video we are going to see how percentages play the relation between percentage problems and linear equations and how they can be used together. This is basically just a continuation to the previous video. So let's see what this guy has to say.
In the previous chapter, we introduced the concept of percentages and explored the principles on which percentages are based. In this chapter, we will use algebra to solve real-world problems involving percentages. It has been reported that in Sweden, 20% of all road accidents involve an elk. Out of the total number of Swedish road accidents in January, if 20% of them involved elks, and there were 24 of these road accidents with elks, then how many total road accidents were there in Sweden that month? To solve this problem, let's let X represent the total number of road accidents in January. We know that the 24 accidents involving elks were 20% of this number. And since the decimal equivalent of 20% is 0.2, we can write this quantity as 0.2x. Since 0.2x is the number of accidents involving elks, we can now create the equation 0.2x is equal to 24. To solve this equation, we eliminate the coefficient of x, 0.2, by dividing both sides of the equation by 0.2. This allows us to cancel the coefficient, leaving us with the equation x equals 24 divided by 0.2, or x equals 120. So, according to our calculations, there were a total of 120 road accidents in Sweden during the month of January. If in February the number of accidents increased by 25%, then how many accidents occurred in February? Let's let X represent the number of accidents in February. The increase in accidents was 25% of the number of accidents in January, or 25% of 120. Since the decimal equivalent of 25% is 0.25, we can write this increase as 0.25 times 120. We can now create an equation which says that X, the number of accidents in February, equals the number of accidents in January plus 25% of that number. To solve this equation for X, we simply complete the arithmetic. 0.25 times 120 is 30. And 120 plus 30 is 150. So 150 accidents occurred during the month of February. This change represents a 25% increase from January to February. If in March the number of accidents returns to the previous amount, what percentage decrease from the accidents in February does this represent? Since the change from February to March is the same size as the change from January to February, it might be tempting to say that this change will also be 25%. However, this is not the case. We want to find the percentage of accidents in February which did not occur in March. If we call the decimal equivalent of that percentage P, then P times 150 is the difference in accidents between February and March. We can now write an equation which says that the number of accidents in March equals the number of accidents in February minus the change in accidents P times 150, or 150p. To solve this equation, we would like p alone on the left side. So we start by adding 150p to both sides of the equation, which allows us to cancel the 150p term on the right. We then subtract 120 from both sides, which allows us to cancel the 120 term on the left. Completing the arithmetic on the right, 150 minus 120 is 30. Finally, dividing both sides by 150 allows us to cancel 150 in the numerator and denominator of the fraction on the left, leaving the equation p equals 30 divided by 150, or p equals 0.2. So the decrease in accidents from February to March is 0.2 times 150. Since 0.2 is the decimal equivalent to 20%, this represents a decrease in accidents from February to March of 20%. Even though the size of the difference from January to February is the same as from February to March, this same value represents a larger percentage of 120 than it does of 150. Therefore, this same quantity represents a 25% increase from January, but only a 20% decrease from February. For our next example, we will solve a problem which involves percentages of profit and loss. For her birthday, Adrian's uncle Monopolis gives Adrian $1,000 to invest in the stock market. Adrian decides to split her investment between two startup companies. The first company, Alaskan Swimwear, plans to introduce a new line of high-fashion swimsuits. Unfortunately, hoping to capitalize on an underdeveloped niche market, they introduce their swimwear only to stores located north of the Arctic Circle, and the stock drops to 50% of its initial value. The second company, Smellophone, has developed a smartphone which not only transmits sounds and pictures, but can also transmit smells. Its stock triples to 300% of its initial value. In spite of her bad investment in Alaskan Swimwear, Adrian's brilliant Smellophone investment more than makes up for her loss. And the total value of her $1,000 stock portfolio increases to $1,500. Knowing only this information, is it possible to determine how much money Adrian invested in each company? When solving algebra problems, it is sometimes helpful to create a table of known and unknown values. Let's create a table for the initial and final values of each investment and Adrian's total investment portfolio. We know that initially her portfolio had a value of $1,000, and that the portfolio's final value was $1,500. Although we don't know the initial value of either investment, we do know that the final value of the Smellophone investment was 300% of its initial value, and the final value of the Alaskan Swimwear investment was 50% of its initial value. If we let X represent the initial value of the Smellophone investment, then the initial value of the Alaskan Swimwear investment must be 1,000 minus X, since both investments totaled $1,000. The final Smellophone value is then 300% of X, or 3X. And the final Alaskan Swimwear value is 50% of 1,000 minus X, or 0.5 times 1,000 minus X. We can now create an equation which states that the final value of the Smellophone investment plus the final value of the Alaskan Swimwear investment is equal to the final value of Adrian's total portfolio. To simplify this equation, we can use the distributive property to distribute the 0.5 multiplier to the two terms in parentheses. And completing the multiplication, 0.5 times 1000 is 500. To simplify further, we can combine all the terms containing x. To do this, we rearrange the equation so that all the x terms are on the left side, and the terms without x are on the right. Subtracting 500 from both sides of the equation allows us to cancel the positive and negative. Combining these terms, 3x minus 0.5x is 2.5x. 100 can be eliminated. This allows us, leaving the or x equals 4 into the expressions in our table. Now we can substitute to find the size of each initial investment. We see that Adrian's initial Smellophone investment was $400, and her initial investment in Alaskan swimwear was $1,000 minus $400, or $600. So far, we have seen how algebra can be used to solve various types of percentage problems, including percentage change and profit and loss. How algebra can be used to solve various types of percentage problems, including percentage change and profit and loss. In the next lecture, we will see how to solve problems involving mixtures of solutions of different concentrations. Welcome to can be used to solve various types of percentage problems, including percentage change and profit and loss. In this chapter, we will see, but what exactly is a solution? And what does it mean to say that a solution has a particular concentration? A solution is a mixture of one substance called the solute dissolved in another substance called the solvent. Often specified as the percentage volume of the solution, which is concentration. Volume percent is usually used as antifreeze. 25 volume percent solutions, the volume percent concentration by the 100 to get a percentage. For example, if the volume of solute is 80 milliliters and the For example, if the volume of solute is 80 milliliters and the concentration the volume of one solution contains 10% antifreeze, and the other contains allows us to cancel the positive and negative 2's on the left, leaving us with the equation x equals 5 minus 2, or x equals 3. We can now substitute this value for x into our table to find the quantity of fuel to take from each barrel. We see that the quantity to take from the 12% barrel is 3 quarts, and the quantity to take from the 2% barrel is 10 minus 3, or 7 quarts. So by using algebra to calculate the quantities of the two fuel mixtures to combine, AV can complete his yard work. Welcome to YU. In the previous chapter, we saw how algebra can be used to solve problems involving mixtures of solutions. In this chapter, we will see how to solve problems involving other types of mixtures. Adrienne Scienstein has taken a part-time job managing her Uncle Monopolis's coffee shop. The shop sells 2 different types of roasted coffee beans at 2 different price points. Their very expensive Tasmanian roasted coffee, handpicked by specially trained wombats, sells for $31 per pound. The shop also offers an inexpensive coffee, roasted at the White Sands Nuclear Testing Range, for $3 a pound. Adrienne thinks that a moderately priced coffee might appeal to a broader group of customers. She decides to mix the 2 types of coffee beans to create a special blend costing $10 per pound. To do this, Adrienne must calculate the quantity of each type of coffee bean needed to create a pound of coffee costing $10. As we saw in the previous chapters, this problem can be organized by creating a table. In the first row of the table, we will list the price per pound of each coffee. We know that the Tasmanian coffee costs $31 per pound. The White Sands Nuclear Roast costs $3 per pound, and the blend we wish to create must cost $10 per pound. In the second row, we list the weight of each coffee to mix to create 1 pound of coffee blend, which costs $10. If we let X represent the weight of the Tasmanian roast, then the weight of nuclear roast must be 1 minus X, since the combined weight of Tasmanian roast plus nuclear roast must be 1 pound. In the third row, we will list the total cost of each coffee, given the price per pound and the weight. The cost of the Tasmanian roast is $31 per pound times X pounds, or 31X dollars. Likewise, the cost of the nuclear roast is $3 per pound times 1 minus X pounds. Since the combined cost of the 2 coffees in the blend must be $10, we can create an equation which says that the cost of the Tasmanian roast plus the cost of the nuclear roast equals $10. We can now solve this equation for X. We start by distributing the 3 to the 2 terms in parentheses. 1x minus 3x to get 28 equation. Allowing the equation 28x equals 10 minus 3 and divide both sides by denominator equation after. So to create 1 pound of a $10 per pound blend, Adrienne must mix 1/4 pound of Tasmanian roast with 1 minus 1/4 or 3/4 pound of nuclear roast. We can check our calculation times that comes in pounds. 4/4 equal to roasts is $10. Our calculations appear to be correct. Our next example illustrates how algebra can be used to solve problems involving mixtures of items selling at different prices. The YU Entertainment Committee is planning a concert of the world-famous bagpipe quartet, Alistair, Ian, Angus, and Clyde, concert hall which seats 1,000 people. Normally, tickets sell for $50 a seat. However, to be sure that the 1,000-seat auditorium is completely filled, the committee has decided to offer a number of discounted tickets at $30 a ticket. The total revenue collected from ticket sales must be at least $45,000 in order to cover the cost of the performance. The entertainment committee therefore needs to know how many discounted tickets can be offered and still collect $45,000, assuming that a total of 1,000 tickets are sold. Fortunately, using algebra, we can calculate how many discounted tickets can be sold and still collect $45,000. Once again, we can organize this problem by creating a table. In the first row of the table, we list the ticket prices for discounted and non-discounted tickets. In the second row, we list the number of discounted and non-discounted tickets which will be sold. If we let X represent the number of discounted tickets, then the number of non-discounted tickets will be 1,000 minus X, since the total number of tickets is 1,000. In the third row, we list the revenue generated by each type of ticket given the ticket price and the number of tickets sold. The revenue produced by the discounted tickets is $30 times X tickets, or 30x dollars. Likewise, the revenue produced by the non-discounted tickets is $50 times 1,000 minus X tickets. Since the total revenue generated by both types of tickets must be $45,000, we can create an equation which says that the revenue from discounted tickets plus the revenue from non-discounted tickets is equal to $45,000. We can now solve this equation for X. We start by distributing 50 to the two terms in parentheses. X, leaving the negative 20. We get X equals 250. So 250 discounted tickets can be sold, and 1,000 minus 250, or 750 non-discounted tickets can be sold. We can check our calculations by multiplying the tickets 75,000 quantities of discounted plus non-discounted tickets is $45,000. We know that our calculations are correct. In the last several lectures, we have seen how to create linear equations to solve various types of real-world problems. In the next few lectures, we will explore algebraic methods which we can use to create parallel and perpendicular lines.